Welcome to The Explainer. Today, we're going to decode the fundamental processes that change literally everything around us, from the food we eat to the very air we breathe. It is time to pull back the curtain on chemical reactions.
So let's kick things off with a little mystery, one that you actually see every single day whether you realize it or not. You know, all these everyday events, some of them kind of frustrating, some of them delicious, they're all connected by this powerful invisible process. And that secret? It's the chemical reaction. Okay, so there's your textbook definition. Anytime a chemical change happens, boom, a chemical reaction has taken place. But how do we actually know one is happening? What are the clues we should be looking for? All right, let's get into it. To really understand reactions, you've got to think of yourself as a detective, on the hunt for evidence that a change has actually occurred. So what's this evidence we're looking for? Well, our detective kit has 4 key clues. You're looking for something changing its form, like a solid to a liquid. Or maybe a sudden new color appears out of nowhere. Or you see gas bubbles fizzing up. Or you just feel a noticeable change in temperature. If you spot any of those, you have almost certainly found yourself a chemical reaction.
Take burning a magnesium ribbon, for instance. This single event, it checks off multiple boxes on our list. The shiny metal ribbon turns into a white powder. That's a change in state and in color. And that dazzling white flame, it's not just for show. That's a massive change in temperature. It's just a perfect, dramatic example of a chemical reaction in action.
So how in the world do we describe these complex events without having to write a whole novel every single time? Well, chemists, being pretty efficient people, they developed a kind of universal shorthand to get right to the point.
I mean, writing it out as a full sentence totally works, but it's a mouthful, right? There has got to be a better way. Now, this is a big improvement. It's called a word equation. On the left side, you've got your starting materials, the reactants, and on the right, you've got your final substance, the product. That arrow in the middle just shows the direction of the change. Simple. And this is where the magic happens. This brilliantly shows the power of a true chemical equation. By using chemical symbols, we have a clean, universal language that tells the entire story of the reaction in just a few characters. So much better. But there's a fundamental rule we have to follow. It's a law of the universe, really. And our simple equation, well, it doesn't quite obey it yet. The law says you can't just create or destroy matter. Whatever you start with, you have to end with, just, in a different form. So here's the crucial point. For an equation to be true, it absolutely must be balanced. The number of atoms for each element has to be identical on both sides, the reactant side and the product side. So let's see how that's done with a more complex example. Okay, we're going to balance the equation for iron reacting with steam. The process is a lot like solving a puzzle, and it has just a few key rules. We'll list out our atoms, start with the most complicated part, and then use what are called coefficients. Those are the numbers we place in front of the formulas to make both sides match. Now, it's super important that we never ever change the formulas themselves, just the number of them. Our first count here shows the problem pretty clearly. The number of iron and oxygen atoms is completely different on the reactant and product sides. For this equation to follow the laws of physics, we've got to get these numbers to match up. All right, let's start with the oxygen atoms. The product side has 4, so we need 4 on the reactant side too. We do that by putting a big 4 right in front of the H2O. Now our oxygen is balanced, but we've just created a new problem. That 4 also multiplies the hydrogen. So now we have 8 on the left and still only 2 on the right. Time for the next step. That's an easy enough fix though. To balance out the hydrogen, we can just place a 4 in front of the H2 over on the right. And just like that, we have 8 hydrogen atoms on both sides. Okay, oxygen is good, hydrogen is good, just one piece of the puzzle left. And the final step is iron. We've got 3 atoms on the right, so we just need to pop a 3 in front of the Fe on the left. And there we have it. If we do a quick final check, 3 iron, 8 hydrogen, and 4 oxygen atoms on both sides. It is perfectly balanced. Our equation now correctly describes what's happening in reality. So now that we have the language down to describe these reactions, we can start to explore their different types. You could even think of them as having different personalities. 2 of the most straightforward types are combination and decomposition. Combination reactions, they build things up, like burning coal to make carbon dioxide. Basically, 2 things become one. Decomposition is the exact opposite. One complex thing, like limestone, breaks down into simpler parts.
Then you've got displacement reactions. Think of single displacement as a single swap, where a more reactive element, like iron, comes in and kicks copper out of a compound. Double displacement is more like two couples swapping partners, where the ions between two different compounds just trade places to form two totally new compounds.
So what does any of this molecular matchmaking actually matter? Well, because this invisible world of reactions is happening all around you and inside of you every single second.
You know that rust you've seen on an old nail or a bridge? That's corrosion. It's basically a slow-burn chemical reaction, an oxidation reaction to be specific, where iron reacts with the oxygen and moisture in the air.
Here is another real-world puzzle that chemistry solves for us every day. And I promise, it's not just to make the bag look bigger and trick you.
The real secret is to stop a reaction called rancidity. You see, the fats and oils in chips will react with oxygen, and that makes them taste stale and smell just awful. So, by flushing the bag with unreactive nitrogen gas, manufacturers get rid of the oxygen and stop that reaction before it can even start. It's a fantastic, everyday application of chemistry.
You know, even the simple act of breathing is part of a complex reaction called respiration, where the glucose from your food reacts with oxygen to give you energy. So from the very energy that powers your body to the fresh taste of your favorite snack, chemical reactions are the secret architects of your reality. What will you notice next?